Hi, I'm Will, and this is my lab 4 report. For this lab, we were tasked with first observing a mass on a spring in Tracker, and then modeling that data. Our model was also used to calculate all the energies affecting the system. We were also tasked with comparing how our model holds up against our observed motion. In this case, we were simulating a model similar to a climber hanging on a rope. The system was the ball with the mass, and the surroundings were the spring and the Earth with its gravity. Later, we will see that this model does in fact accurately represent our observations when we compare them side by side. Next, I would like to talk about some of the important physics concepts used in this lab. Firstly, Newton's second law is essential to modeling. At its most basic form, it is force equals mass times acceleration. However, that can be easily transformed into the velocity update formula as shown on the slides. That can also be further transformed into the position update formula. The position and velocity update formulas are essential to modeling motion in GlowScript. The next set of essential formulas are from the energy principle. We needed to predict all the energies acting on the system, which included kinetic, gravitational potential, and spring potential. Finally, although not shown, I used the Earth's gravitational force formula and spring force formula to calculate net force for the model. Now I'd like to do a quick overview of my most essential changes in GlowScript. On the left side, you can see the changes I made to accurately model the motion of the spring using the position and velocity update formulas. I also changed the glow script to update the non-constant force of the spring and update the changes in the energy on the system. On the right, you can see how I created the initial values for the spring force and energies. Another change I made was editing the code to accurately represent the initial conditions found in the observation. This included the initial position, velocity, gravitational constant, spring constant, and relaxed spring length. Here are the graphs comparing both the x position and y position between the model and the observation. The model is very close to the observation, however there are a few differences. On both graphs, the model is slightly ahead of the observation. I think this may be a result of the poor frame rate on the observations. The frame picked as the start of the experiment likely isn't the actual start of the motion, which causes a deviation. It's likely that the start of the actual motion happened between frames and the actual observation, which causes deviation. The poor frame rate also changes the shape of the observation graph as seen. It makes it much less smooth and a bit more choppy. As you can tell, the red one has some harder lines compared to the smooth blue one. Another thing to note is the difference in amplitudes. On the x position graph, the experiment has a slightly greater amplitude, while on the y position graph, it is slightly lower. This is likely a result of human error in Tracker and estimation error from the force of gravity formula using the 9.8 constant rather than actually using the force of gravity formula, and then not accounting for air drag. The error is quite small in the scope of the experiment, but the scale of the graph does make it seem a bit more significant than it really is. If you look closely, it's only like maybe like 0.01 to 0.02 off, which really isn't that much in the scheme of things. Um, and here's my energy graph. Um, as you can see, the change in energy, which is the orange line, change in overall energy is at a constant zero, while the other energies move in response to each other and keep the change in energy zero. And as you can see, if you were to pick a single point on the x-axis, if you were to add all the numbers up between the red, the green, and the blue lines, you'd see that they'd all sum up to zero, with the red line being the change in gravitational potential, the green line being the change in spring potential, and the blue line being the actual kinetic energy. Next, I would like to finish the report with some analysis. Firstly, we were asked if the energy principle was satisfied. My answer is yes. As shown on the previous slide, all of the energy summed to zero and remained that way for the duration of the model. This was a result of the energy in the system and the energy of the surrounding being equal and opposite, which was shown on the previous slide. In short, conservation of energy was held because delta E stayed zero for the entirety of the model. Next, we were asked to determine the oscillation periods of the observation. I found the oscillation periods by finding the time between apexes on both the y time position graph and the x time position graph in Tracker. This gave me roughly 1.5 seconds of oscillation time. It makes sense that both were very close together. When you look at the graph, you can see it's a diagonal elliptical shape, meaning that it was at both its furthest xy points at the same time. The picture of its path is shown here. You can see in the bottom, it kind of made an ellipsis towards the bottom right and the top left, and that would be because that's the furthest point on the x-axis in one direction and the y-axis downwards, and then opposite on the left, the upper left. And that would make sense for um, the apexes of one graph to meet the valleys of the other. Thank you for listening.